This is another quick and dirty little video about stress. Here we're going to think about some basic ideas about signs of shear and normal stresses. You will recall that we are going to be working on a small cube of material, and the coordinate axes and the center of the cube are coincident. So the faces of the cube are perpendicular to each of the coordinate axes. We've named these axes 1, 2, and 3 in this illustration. The 3 axis is pointing right at us. Here's a shear stress that is acting on the 1 plane, and it's pointing in the 2 direction. We use this symbol that looks a bit like a harpoon to designate shear stresses in these little mechanical diagrams. We would call that shear stress sigma 1, 2, or in longhand, this is the shear stress acting on the 1 plane in the 2 direction. Now that's the first of several stresses that we're going to have to represent on this cube. On its opposite face, we have a symmetric shear stress. If we applied those shear stresses to the cube would start to move. Now this is a static analysis, so we can't let the cube move. But just for the moment, imagine that you put your hands on the sides of this cube and you moved your hands in the direction indicated by those little harpoons, those little half arrows. What would happen to that cube? What direction would it move? Well, it would probably rotate in that direction. But this is a static analysis, so if we have a tendency for the cube to move in one direction, we need to counteract it with an equal and opposite set of forces to keep that cube static. If we had a different set of shear stresses on these faces, these vertical faces, we would have a different sense of rotation in the cube. These 2 senses of rotation, clockwise and counterclockwise, have been assigned a sign. Shear stresses that might induce an anti-clockwise rotation are positive shear stresses. Shear stresses that might induce a clockwise rotation are negative shear stresses. In order to keep that cube from rotating, we need to balance the positive shear stresses on the vertical faces with negative shear stresses on the horizontal faces. But that's not enough. If we have shear stresses on the horizontal faces that are of a different magnitude than the shear stresses on the vertical faces, we won't have balanced the stresses. If sigma 1, 2 has a magnitude of A, we know by symmetry on its opposite face there will be a magnitude of A. What is the magnitude of sigma 2, 1? If the vertical faces are experiencing a shear stress of A, the horizontal faces will have to have that same magnitude of shear stress, otherwise the cube is going to start moving. So the magnitude of sigma 1, 2 must be equal to the magnitude of sigma 2, 1. We use symbols that look like absolute value symbols to indicate the magnitude of these 2 quantities. So the magnitude of shear stress sigma 1, 2 is equal to the magnitude of shear stress sigma 2, 1. The magnitude of the shear stress on the 1 plane in the 2 direction is equal to the magnitude of the shear stress on the 2 plane in the 1 direction. Jumping back to 3 dimensions for a moment, we see that on these 3 faces that are visible to us, we have a collection of stress components related to the total stress vector on each of those 3 planes. The cube has 6 faces, though. If we know the stresses on these 3 faces, we also know the stresses on the opposite faces. So we really only have to work with these 9 stresses that you see represented in this illustration. We've got 2, 4, 6 shear stresses, and we've got 1, 2, 3 normal stresses. The 6 shear stresses are not independent. To conserve angular momentum, conjugate pairs of shear stresses must be equal in magnitude. So sigma 1,2 equals sigma 2,1. Sigma 1,3 equals sigma 3,1. Sigma 2,3 equals sigma 3,2. On the other hand, the three normal stresses acting on any point parallel to the coordinate axes are independent of one another. Each of them might be tensile, zero, or compressive. What does that mean? Here is a normal stress, and the stress vectors are pointing away from the center of mass of the cube. We call this a tensile normal stress, or simply tension. The sign convention used here is consistent with traditional usage in engineering and mechanics. If the normal stresses acting on this cube are directed inwards towards the center of mass of the cube, then we call that condition a compressive normal stress, or compression. This sign convention is consistent with the traditional usage in engineering and mechanics, so we consider a compressive normal stress a negative stress. So here again are two important ideas that you should take away from this little video. The three normal stresses acting at any point parallel to the coordinate axes are independent of one another. Each might be tensile, zero, or compressive, and each can have its own magnitude. They are independent of each other. The 6 shear stresses are not independent. To conserve angular momentum, conjugate pairs of shear stresses must be equal in magnitude.